Good morning again, class. This is the second part of the review. We're going to be covering Chapter 2. We're going to talk about limits and really focus on the definition of the derivative. So in 2.1, we introduce this idea of what a limit is. And we introduce limits first as they approach a value c. Okay, what is the function doing? Okay, what happens when it approaches some value? Okay, and it is close to a single real number L. However, there are ideas that what is happening in the function as x approaches c from the left, or as x approaches c from the right. There are times when maybe they're doing different things. So we're really looking at these functions a little bit closer. Okay, the limit as x approaches c from the right is also L, and notice how we're using c plus, and on the previous page we did limit as x approaches c minus, and this is approaching from the left. Okay, limit properties are useful for evaluating limits, and this difference quotient that we introduce here is really the beginning of the definition of a derivative. But there is, if you notice, we typically can get an indeterminate form. If you have 0 over 0, you need to do some algebraic simplification like factoring and reducing to evaluate this type of limit. If you get something where the denominator is 0, right, d of x is 0, you probably have to do some algebraic simplification. All right, in 2.2, so 2.1 we talked about a limit at c, right, as x approaches c. In 2.2, what happens when the limit approaches infinity or negative infinity? Okay, what is the function doing? Is there a limit? Does the function go on to infinity, or does it reach a maximum or a minimum? The behavior of a polynomial is described in terms of limits at infinity. Oh, I think I missed on the previous page is the vertical asymptote. And so typically when we're looking at limits, we're looking at the vertical asymptote or the horizontal asymptote. And again, you can look in 2.2 on how to find those. Continuity. Is there a break? Typically, rational functions might have a break or a hole, but here are some rules if a function is continuous. Okay, f is continuous at c if the limit at this function exists. That's number one. If f of c exists, if you plug in the original function, forget about the limit, plug in c to the function and it exists, and then is the limit as x approaches c equal to when you plug it in. Okay, all of these three things have to happen in order for it to be continuous. Okay, the derivative. All right, here are the interpretations of a derivative, and they're all stated in red. I'm going to read them. The average rate of change. It's typically how you read a derivative. The instantaneous rate of change. I'm sorry. Typically, the derivative is giving you the rate of change, but the derivative is the instantaneous rate of change. Okay, it's the limit of the average rate as the change in x approaches 0. It is also the slope of the secant line, right? If you have a graph, and that's basically the tangent line. Okay. When we're finding the derivative, there is a 4-step method. You need to know the 4-step method. I will ask you this on the short answer portion. I want to see all of the work for this 4-step method. And again, you can look in 2.4 for what that is. Basic differential properties. Okay. First one, number one, the derivative of a constant function is 0. So what is the derivative of 300? The derivative of 300 is 0. Okay. For any real number, this is the power rule, right? And again, for this is number 2. And for number 2, you can see that, what is the derivative of something simple like x squared? Well, f prime of x is equal to 2x, okay? And you can keep going on. What happens when there is a constant? This is the constant multiple function. So let's say f of x is equal to 3x squared. We can leave that 3 out, right? And f prime of x is equal to 3 times, again, 2x, which is equal to 6x. And the derivative of a sum or difference, okay, is equal to the derivative of the sum or difference. So, for example, what is the derivative of 3x plus x squared plus 4x cubed, right? So then all you do is you take each individual derivative. The derivative of 3x is 3. The derivative of x squared is 2x. And the derivative of 4x cubed, again, you bring that down. So 3 times 4 is 12. And x cubed, this is x to the 3 minus 1 is x squared. So notice you just find each individual derivative and add them up. We didn't really cover differentials, so I'm not going to test you on them. However, their idea of marginal analysis and the average cost, you will have a short answer problem that covers this. I'll ask you basically for the derivatives of the cost, the revenue, and the profit functions.